Hello and welcome to the next video in the series here. We're going to be looking at exponential growth models. The previous models we used were financial models specific. And in this model, this is very similar to the compounding interest one, but it is in a simpler format in that we talked about this. There's A here. This A value is basically your initial amount. B is your base of your exponent, so that's going to include your growth rate. In this case, B is always going to be 1 plus your growth rate, and your growth rate is dependent on time. So in different things, if you're given a growth rate per year, then that's how much it's going to grow per year. If you're given a growth rate per hour, that's going to how much then X is going to be in hours here. Or years, or whatever the value for X is going to depend on the growth rate. Now in this problem, we have a town of population of 55,000. It's growing at a rate of 4.3% per year. And it wants you to write a function for the population and then use the model to estimate how many years it will take the population to reach 80,000. Alright, so here's our model. Y equals A times B to the X power. Now in this case, as I said before, the model A is going to be your initial population, which is 55,000. B is going to be 1 plus the growth rate, in this case 4.3%. So there's 4%, and then there's one more 4.3%. And your X value here is going to be time, so we can put T in there, or we can put X. But X stands for time. X is time in years. Okay, so your model is going to be Y equals 55,000, 1.043 to the X power. That's your model to estimate how many years. Now, what we would then do is put our 80,000 in there for Y. 55,000 plus 0.43 to the X, and we want to solve for X. So in the first part of all of these is we want to divide by your initial amount. So in this case, we're going to divide by 55,000. Your whole thing here, and your whole thing here by 55,000. Now, our right-hand side is going to be 1.043 to the X power. Our left side is going to reduce to 80 over 55, and 8 or 5 goes into both of those. That would be 16 over 11. So 5 into both those reduces to that fraction. Now we're going to take the log of both sides to be able to move this exponent down. So we're going to apply a logarithm. I'm just going to use a regular logarithm to both sides. So I'm going to write log of 16 over 11 equals log of 1.043 to the X power. Now, since I've applied that logarithm, I can then move this exponent in front by that property that says a log with any exponent, the exponent can be moved down in front. So this is going to be X times log 1.043 equals log 16 over 11. And then all I need to do is divide both sides by log of 1.043. And I'm going to get X, which is approximately, let's see what that is, log of 16 divided by 11 divided by log of 1.043. 8.9 years. 8.9 years. Okay, let's verify that on the calculator. We plugged it in, but let's verify it using our graphing calculator. So we're going to put in our 55,000. Now we know it's 1.043 raised to the x power. And we want to verify that that's 80,000. Okay, we're going to set our window, make sure it's big enough. We had this from the previous one. Looks like this is going to be set up okay. 0 to 25. We're going to 100,000, which is going to be above 80,000. We're going to go by 10,000. So I'm going to use this same scale as I had in a previous video. I had this set up. All right, graph. And we can see there's our exponential and there's our linear function. They're going to cross right here. It should be about 8.9. Let's just double check. So I can calculate, intersect, enter. First curve, yes. Second curve, yes. And we want to move it to the left till we get to close to 8.9. 8.7. And our answer is going to be 8.8998, which is what we got on our calculator before. So we verified using the graphing calculator that that's a solution. All right, let's move on to our second example. Our second example here is we have a bacteria that's doubling in population every 5 hours, and we want to find its hourly growth rate. Now, in a problem like this, we would probably use a different model, but they did ask for an hourly growth rate. So since we're using an hourly growth rate and then we're dealing with hours here, we're going to use this model because your x values can be in a time unit that's not continuous. In the next video, we're going to deal with continuous time change rates. But in this case, we want an hourly rate. So we're going to just start with this. It's going to double. That to me means that we're going to have twice as much when we start out with one item, and we don't know the growth rate. So we're going to have B, and that's going to be 5 hours. So this is what we have. So it's really 2 equals B to the 5th power. So in order to find my solution here, I'm going to need to take the 5th root of both sides of this equation in order to get rid of this B to the 5th, in order to do the inverse operation of the 5th power is the 5th root. So we're just going to approximate what B to the 5th root. So in our calculator, we put in the root number, we go to math. There's number 5 that does the root. 5 of 2. So that's going to be 1.1487. 1.1487. So that means my hourly growth rate here in this problem is the values after the 1, because it's 1 plus the growth rate. So my growth rate would be 0.1487, or 14.87% growth rate per hour. Okay, so that's our growth rate per hour. Now, remember B was 1 plus the growth rate. So that's how we figured it out. Now, there is another way to find 2 to the, if you didn't remember the root thing, we can also use the power button, but a root is always 1 divided by the root value. So 1 divided by 5 is our root power. It gives us the same answer there. So either one of those ways is the way you can find the root. All right, now let's use this to help us find the population when it would reach 3,000. So we're going to start a separate problem over here on this side of when it's going to reach 3,000. So 3,000 is our future value. 200 is our beginning value. We know the rate is 1.1487 now, but we don't know the time. So this would be how I'd set up the problem to solve it for time here. So we go through the same process as we did up here. We're going to divide by 200. All right, we're going to get 2 zeros to drop off here. So we got 30. This is going to be 15 equals 1.1487 to the x power. We're going to take the log of both sides. We're going to move this exponent down to the front. So it becomes x here instead of there. And then we're going to divide by log of 1.1487 to get our answer. So this two logarithms divide will give our answer for x here. So let's do that on the calculator and figure out what that is. So we take the log of 15 divided by log of 1.1487. In this case, 19.5 hours. So in this case, we're going to have an answer of 19.5 hours. It would take less than a day to get our population up to 3,000 if it's unrestricted growth. All right, and later on we'll do a model where it is a restricted growth model. All right, so we're going to stop with this example, but then we're going to start with this kind of an example on our next video, and we're going to use a different formula where we have continuous growth. So each formula is modeled depending on what kind of growth we're dealing with. Now, if we know a growth rate per time, then we're going to use this formula. If it's a growth rate that's continuous, we're going to use a different formula, and that's what we're going to do on our next video.